Hello, we return after the coffee break. I think the coffee was very nice. And we start the next session. This would be beginning once more done by Gdańsk University of Technology. The application of simulation-based sensitivity analysis in the preliminary design of network domes. So I think that this would be a little bit continuation of what we've seen before the break. Please keep the time schedule to enable some discussion. Thank you.
Thank you very much. Hopefully you don't have enough of the simulation-based sensitivity analysis, because here I go with the second subject. This time in cooperation with Mr. Legowicz, we have made an analysis concerning the design of network domes. Oh, sorry. Unfortunately, it's not working.
My finger.
Okay, so this time the main aim of the study is to preliminarily design a semi-spherical three-dimensional ribbed dome, network dome, with the best possible solution to its design. Of course, we aim to have maximum stiffness, maximum strength of the structure, and we also aim to minimize the economic cost. So we take, the scope of the study is that we take different ribbed domes geometry and we visualize which ones will be perfect for our study without a simple analysis, just visually. Then for the chosen grids, we adopt the variables that can be treated as random in order to perform the sensitivity analysis. From this preliminary design, from this preliminary analysis, we derive one dome for further analysis, for further investigation. We assemble a parametric model of the dome, we perform the simulation-based analysis, and then we attempt to analyze it and to optimize the layout of the dome under interest. From different three-dimensional ribbed domes, you can see different layouts and different elevations of such domes. So it's really arbitrary to choose which one is the one that we want. So the first choice is architectural based, because we just decide on the diameter, on the height of the structure, on the type of the grid, and for further investigation, upon no clear reason, just architectural, we have chosen these three dome grids, and we decided that we will focus on the semi-spherical one. These are the three models for the domes analyzed. We have a simple ribbed dome, we have a Schwedler dome, and we have a lamella dome. And for each dome, some parameters are assumed identical as the values of angles, so that the grids have a similar amount of elements or a similar geometry. The diameter and the height, the cross sections of every element, and the material parameters. First, we put a test force on the key node to assess how the structural response behaves, what are the forces, what are the displacement. And in Sophistic, we have made a series of simple analyses upon these test forces, in which we have measured deflection, in which we have measured the maximum compressive and tensile forces, measured the maximum stresses, measured or investigated, because we didn't measure it, we investigated the number of elements, the total length of the elements, total mass of the structure, and upon a series of calculations, not only this one presented, we have chosen that the best possible way for a beautiful architecturally and for a designable structure is the lamella type here in violet. For the considered dome, for the considered lamella dome, we have made a full analysis of the numerical problem, of the numerical model. So we have assembled all loads, the dead load, wind load, snow load, and the load of the icing. As you can see, that the dome is now covered, but it's covered a little bit falsely because these elements have no stiffness, these elements have no weight. They're only here to transfer the loads properly from the engineering description to the nodal or to the element forces in order to produce the calculations. And the key results are given here. You can see that for standard loads, a dome of these proportions have a favorable, I would say, response because the safety margin of the ULS combination is very high, and the key displacement is even higher in relation to the safety margin determined by the SLS. Now we transfer to the sensitivity analysis. We assumed that we can change the position of the vertices, and here the position is changed in 4 waves. We add 2, 1, or we subtract 1 or 2 degrees. Then that's how we change the position of not only one node, but of all nodes that lie in this plane, of course. So we elevate or we make them lower, and we see if there's a favorable or unfavorable influence on the structural response in terms of displacements and stresses. We perform local analysis where one level is modified only and the other levels remain unchanged, and we investigate global ones when we take the combinations of the changes and see if a combination is favorable or not. This, of course, produces a high numerical effort. So we have my co-author has made a procedure governed by Python programming language in which the compiler produces a numerical model. So we only input those values that we want to change, and the model is regenerated itself and recalculated itself. So the time consumption of the process is very low, which is the main key for advancing into simulation-based sensitivity analysis, because we take a multitude of models and we have to make them calculate very rapidly. Upon the sensitivity analysis, we have found that some levels really impose a high influence on the response of the entire model. And upon those numerous calculations, we have concern that some levels, as you can see, the level number 7, the level number 8 in the greater extent, and the level 4 and 6 into lesser extent, they influence the structure much. And as you can see, some levels need to be dropped down and some levels need to be elevated. And this is an interesting question, interesting remark. As you can see, those advantageous levels are now transferred into the real geometry. As you can see, the geometry is not perfect in terms of the layout of the nodes upon the height of the structure. And with different combinations, again, we determined that this may be the quasi-optimal. So upon a number of simulations, we find this simulation to be the most beneficial for us. These nodes are not changed in the position of 1 or 2, but the dimensions are slower. The modifications are different in order to capture the equilibrium between the state of the structure, so the stresses or the displacement, and the cost to elevate, to construct such a dome. And as you can see, for this quasi-optimized dome, every tensile force, every compressive force was observably lower. The actual stresses are lower and the safety margin increases, and the safety margin of the serviceability limit state, which is crucial in domes, by the way, is also elevated. So now we should take a look at the cross-sectional values and modify the cross-section in order to make the margins lower and to make the construction, make the structure more money-consuming. As you can see, in conclusions, different grids have a significant effect on the structural response, so the choice should not only be done by actual architectural considerations. The type of the model itself make problems, so having a model which is trustworthy is very important. The structural response is sensitive to asymmetrical loads as snow, because in order to have different results, we have moved the snow load upon the structure and the structural response also. And the disturbances also implement changes in the state of the structure in terms of stresses and strains. Also, just one more thing. If we imposed the changes onto other types of domes, we can see that without any further sensitivity analysis, just adopting the solution possessed for the lamella dome to other domes, the response of the domes is better, also is better. So we suggest that the solution may be transferred to other similar domes with lesser extent of calculations. And the future plans, as you can see, because we are now trying to make the sensitivity analysis take into account a multitude of different factors. Thank you very much for your kind attention.
Thank you very much for your interesting second presentation. We have some time for discussion. So if you would like to ask the author or make the comments, you are invited to do that. If not, my comment is that finite element method solver Abacus has, maybe you know, some option called sensitivity analysis that is very specific computer system, as you know. So you could make a comparison to your Python programming with Abacus system. Unfortunately, robot, very popular in civil engineering, let's say, does not enable to do that.
We have made this. I didn't say, but we have compiled the FA model in Sophistic. Sophistic is a standard design office program for modeling such or similar structures. And we have decided on Sophistic because it enables the transfer of the data from Python to create models, which is impossible, for example, in robot, or which is very hard in RFM. But I know that such analysis techniques are present in other models, but for the time being, I did not make such comparison, but I am very willing and able to do such comparison in the future.
Thank you very much. Once more, this sensitivity module in Abacus has been implemented by Polish scientist Piotr Kowalczyk from IFTR PAS. Thank you very much. We have the second presentation. Żyliński and Górski. It is called Deformation. It is called Deformation of a shell of a fuel tank caused by non-uniform soil settlement. We all know that non-uniform soil settlement is a big challenge for civil engineers, so I hope that this would be interesting too. Please.
Okay, so Ms. Chairman, thank you for introduction. Ladies and gentlemen, I would like to present you the topic which is very close to my engineering field, which I am dealing every day, and it will be a quasi-theoretical and engineering approach presented here. That's why this presentation is divided into two parts. First of it is dedicated to the deformation of fuel tank for a shell caused by some spatial parameters for stiffness, yeah. And the second thing is approach which allows engineer to use the probabilistic approach and random field interpretation, but in the, let's say, very easy and practical way, yeah. Okay, so the first example is an existing tank which was built many years ago, and it is equipped with floating roof and some other apparatus like stairs and so on. And its capacity is quite huge because it's 50,000 cubic meters. And by the deterministic approach, it was designed using EN 14015 and Eurocode for stability of shell structures, which is very good known in the engineering field, yeah. And then to implement the sensitivity analysis, a 3D model of this tank was built in Z-Soil, which is a dedicated software for soil and structure interaction between of them. And we can see that these KZ parameters were evaluated upon the real measurements of the so-called boreholes, yeah, which were drilled during the field testing, and each KZ represents different stiffness modulus, yeah. And also, together with this Z-Soil model, Python was used to perform many iterations, but it will be described later on. Here we can see the real borehole scheme of these 5 different areas, and we can see that the variation of the stiffness moduli is quite big actually. In the below part of the table, we can see that these values were summarized and then used in the sensitivity analysis as a basic input data. So what was actually compared? To compare the impact of the changes of the stiffness moduli, there were checked 3 things. First of it is the middle node of the foundation in here. The second thing is the sum of vertical displacement of this annular nodes at the bottom, yeah. And the third thing, the third compared parameter is deformation horizontal in the local base of the stiffening ring on the top, because too bigger deformation can cause a clashing of this floating roof cover, yeah. And the sensitivity was divided into 3 cases. First case assumed that all the KZs were averaged, and all of them were independent in case of different KZ parameter. And we can see some results for the middle node displacement and for the annular plate displacements, yeah. The second case was considered in a more widely dispersion of the input data, because the parameters were considered as with 40% of plus minus variation of the input data. And we can also see some results for the bottom and annular plate vertical settlements. Third case was the most interesting. In case of the deformation, we can see that this shell deforms non-uniformly, and here there are some comparison tables. How does the variation of the input data influence the output, which is the vertical displacement of bottom and annular plate, yeah, results. So for this KZ1 and KZ2 parameters, we can observe that for the KZ1, a very big variation of the stiffness moduli. The peaks of the displacements are also are very high, because they tend to value of 25 centimeters, yeah. And if we consider only this this region as analyzed in sensitivity terms, yeah, we can see that the results are not varying very much, okay? The second idea was to compare KZ2 and KZ4 parameters, areas actually, which are at the diagonal of the middle node of this tank, and we can see that the impact is lower, yeah. And the third thing is the deviation of the top ring by means of variation of the input parameter. And for the very high dispersion of the results of the input data, we can observe that the change is either nonlinear and quite big. But however, we can see that these values do not exceed 2 centimeters. So I'm having these results creates a thought if there is a necessity to create some useful and very easy tool to implement the random approach and probabilistic input data model. Yeah. So therefore, this simple model of brick was created to check if some reduction can be implemented, and we can see that this subdomain, which will be analyzed as random, has dimension 10 by 10 by 10. And to see what's the impact of the probabilistic approach on that, simple random field correlation function was implemented with different decay parameters. And decay parameters, let's say, are describing if surrounding values are highly or less correlated. So for this first line, you can observe that the correlation is very high, decay parameter is very low, and for the last line is very low. Yeah, and then by usage of this auto regression function, 200 models were built. And this is the representation of a simple random field cube by means of graphical scheme, let's say, yeah. And for that, 2,000 samples, the models were calculated using batch processing together with Python and ZSoil, and we can see that the convergence of the results is quite good, even for such low number of samples, yeah. But then to compare if decay parameter has some impact on the results, we can observe that for the deterministic approach, which is represented by the mean value in here, the results are quite the same. But if we consider standard deviation, which is describing the probabilistic approach, we can see the huge difference with the output of the response of the structure by means of probability, yeah. So therefore, this diagram was derived to see what's the, let's say, dependency and the impact between the different decay parameters to the standard deviation. And it was approximated by the logarithmic function. But this diagram actually tells that there's a necessity to use some different kind of approach, which was implemented in here. And this subregion was divided into 125 elements, 8 by 8, 8 in each one. And in this case, it is very useful for the engineer because he can implement the input data into the software without special knowledge to the, let's say, how to generate the random field and put it inside the complicated model, yeah? And the results for that, 200 samples as well, as we can see here, are very converged, even for the less number of samples. But to see if the discretization was done correctly, a different number of division of this subregion was introduced, yeah? And if we consider non-correlated or highly correlated division, we can see that in this case, the approximation of the results can be done by the linear function. And what is more to take as a conclusion from this kind of analysis is that we can estimate and change the whole subdomain for, let's say, such complicated cases as this big tank, with the usage of division, for example, as proposed here, by 12.5% of the whole subdomain. Yeah. And here we can also observe the dependency between the standard deviation and the number of discretization. But as previously, mean value is also very similar. So it turns that for the deterministic point of view, we can have like misleading results. But when we consider more widely with, for example, lack of many input data, and we have to build some probabilistic model, we can derive directly that it's no necessity to build the whole domain independently, but that we can reduce it somehow. Yeah. And actually, this proves that this approach can be implemented into the 3D model of this tank, and it will be performed soon. However, due to the workload, it wasn't done yet, but will be as soon as possible, and I hope the results will converge as well. And yeah, that's the last slide. So thank you. I think I fit into the schedule. So.
Thank you very much. Maybe some of you have some questions. Yeah, okay. Just a moment, I will.
Yeah. Okay, so to comment this, this is the preliminary research which was done to assess if we can use somehow of reduction methods to implement them into the full-scale model. And of course, I agree that interaction between the subcell and the tank is crucial, but that's why we have computed the sensitivity input parameters to assess which are relevant or not. And yes, it's not the general comment for all of the tanks, but in this specific one. But yeah, I agree with you.
Thank you. Maybe anyone else? If not, I have two comments. Oil companies are very nice for civil engineers because of two reasons. The first reason is the money. They sign any bills. But the second is they understand very well probability. Maybe you know, maybe not. They're looking for the oil in the subsoil by calculation of probabilities. So mean value standard deviations are inherent in any computer programs internal in oil companies. I have small experience with Shell company. They ask if you are interested in probabilities. Yes, okay. So you are with us. Thank you very much.
Thank you.
Now we skip to the third presentation. This would be delivered by Professor Walentyński from Silesian University of Technology. The other authors are Agnieszka Padewska-Jurczak and Piotr Szczepaniak. And the title of the presentation would be Experimental and Numerical Analysis of Airflow. This airflow around two cylinders angled to the direction of the wind. Please.
Thank you, Mr. Chairman, ladies and gentlemen. I would like to present a work mainly done by my former students. Dr. Agnieszka Padewska-Jurczak was my student doing the engineering physics. Piotr Szczepaniak did his master and physics connected with that topic few years ago. I also would like to tell you that afternoon a presentation from our department will be done by my PhD students, current of them. Among them is Mr. Wiśniowski, who is sitting over there. And as we know, the success of a teacher is a success of a pupil. So Dr. Szczepaniak was, can I see the next slide? Okay, so he made his research on building such tunnels built of cylinders and torus in many places. This is a very big structure made in Slovakia. And in such big structure, one of the problem is not only the structure itself, but also the wind. And as you can see, modeling of such problem is and designing the structure is a very complicated thing. So as Dr. Padewska-Jurczak is very interested in the problem of the wind, so they together worked on that problem, but they met several calculations problems connected with that. So finally, they, with cooperation with Slovak National University, Technical University in Bratislava, and Professor Hubowa, who is standing on this picture, made the research in the wind tunnel in Bratislava. So here you can see outside and inside of the tunnel when they made the research several 2 or 3 years ago. So they made research, experimental research on the behavior of the 2 tubes, which are presented here, mainly because this problem is not well described in Eurocode. And in this case, they observe very large Reynolds number. So they analyze that two tubes, which were in different distances, and observe what will be interaction between them and what will be answer, mainly to find the proper parameters in the numerical analysis. So here is an example. They use a finite volume method. Here you can observe what is a mesh of this problem. And according to the research on this slide, you can see a comparison of what is you can see in Eurocode, and quite different results carried from their research. They found that there is a crucial importance of distance between wet pipes, and the results were quite different. So that problem is and here you have the results of the numerical calculation, velocity vectors, and pressure distribution over the cylinders at a speed of 19.5 meters per second. The conclusion of the research is as follows: that numerical finite volume method of course, with use of computational fluid dynamics model, made it possible to test, to find the and to make the reliable analysis of the wind flow with high velocity in structure. And the highest value of the forces occur as a delta equal to 1,000 millimeters. They observe also that due to the wind, that pipes there was a suction between them, and that values differs significantly from the values given by Eurocode. And it also, Eurocode do not give information what is the influence if that pipe direction of the wind is not normal to the structure but with some angle. In the case of speed of 90.2 millimeters, there was a clear division of smaller pressure values in front of the cylinder. In case of lower speed, the division is hardly perceptible in the difficult model. We are planning further investigation. In the moment, we are working on the Mr. Wiśniewski is working on the aerodynamic weight of this. But we also make to complete analysis. It may be necessary to take into account connectors of the platforms and other elements, but this is a matter of time and, of course, of money. That phenomenon of a vibration of a circular cylinder in the trace of another cylinder is also a matter of our interest. So I would like to thank you. We are from the Department of Mechanics and Bridges. I am the chairman of that. So it was prepared by, but the main author is Dr. Padewska-Jurczak. And if you will have any questions further, so I will give you contact with her. Thank you very much.
Thank you very much for this presentation. It is right now open for a discussion. Maybe, oh yes.
Thank you, Mr. Professor. Thank you, Mr. Chairman. And I have only one question about maybe introduction of the mass of surrounded fluid as a wind. If it was also investigated, this the fluid, the mass of the wind in dynamic investigation. Did you apply this? Thank you for the answer.
The precise answer for that I will ask Dr. Padewska-Jurczak about that. I suppose that it was like that, but in the end I would like to tell you if you will have any problems connected with water slides. So the names of that two people, especially Dr. Szczepaniak, is probably the best specialist on it and practitioner, not only in Poland, but in the world.
Thank you very much. Just a moment, Professor Szafran.
I just want to ask you, because you have mentioned that in the Eurocodes there's no task with the different angles of the wind direction for two tubes, right? But there is actually there is a task with two cylinders at all?
Generally, for that problems, you can find in Eurocode the task that for more complicated problems when described in Eurocode, you should take an advice from the specialist of wind problems. So This information given Eurocode is very poor.
So thank you very much. If anyone else, I don't see anyone, I would like to say that interfacing of CFD and finite element method static analysis seems to be very popular right now because of the weakness of Eurocode 1.4, and we all know that most probably. Thank you very much. Next presentation, we postpone structural bionic system design and numerical analysis. Very interesting. However, the author is absent. And the last in this session, number 2, would be by Andrzej Rutkiewicz and Professor Leszek Małyszko from Olsztyn. Results of own experimental tests of a Tensegrity Simplex under static loading. I expected such a presentation, so please start.
Thank you very much, Mr. Chairman. At first, I'd like to thank you for the opportunity to be here and to say a few words about my work. I've arrived from Olsztyn. The subject of the presentation was said before. This is the scheme of the presentation. In general, it is an experimental laboratory work. It is an experimental work, a test of a compression test of the most well-known Simplex, the most well-known Tensegrity unit called Simplex. The test was performed with different initial self-stress levels, and the scheme of the presentation is, as can be seen, the first point is a few words about the Simplex, the second is about the methodology, and the third and closes the presentation with results and conclusions. The Simplex is a model which is built with 3 struts, so the members which are load-bearing in compression, 6 base cables, and 3 cross cables. In general, it is characterized by 1 infinitesimal mechanism, and it is a kind of movement where the upper base is rotating along the vertical axis Z versus the lower base. This is the infinitesimal mechanism for the Simplex. And also, it is characterized by 1 self-stress state. It means you just have to, we just have to change the length of 1 element in order to induce the pre-stress. Closer? Okay. Thanks. Of course, in this test, we also have to consider the external loading F. This is the picture of the physical model, which was tested. It is approximately 1.2 meter high and 50 centimeters in diameter. Actually, there were 2 versions of this module, namely the one which has I call it stocky struts, where the slenderness was approximately 94. And the slender struts, which had slenderness above 300, which is very high. The pre-stressing mechanism was created by the Roman screws, which were attached to each of the 3 cross cables, and also a force transducers were attached to every one of the 9 cables. The first transducers were built by us, and they were water cut from a steel plate. And the principle of work was the Whetstone half bridge. When we have 2 active arms, it means that we have 2 strain gauges, which are glued on the inner surface of this body of the force transducer. Because the tensometric bridge, which is shown in here, it is an old unit, but generally it gives readouts as strains. Of course, not strains, but maybe basically an electric current, but we can read strains. So we had to perform a calibration, which was done on a universal testing machine to obtain the chart of a force versus the strain value and as well the temperature calibration, so the strain versus the change of the temperature. Also, because the model is pretty complex, by complex I mean that we have many different elements and connections. We had to perform a compressive test on the struts to find the, I would say, vertical stiffness. So the relation between the force and the vertical displacement. For the stocky struts, this relation is shown in here, and for the slender struts is shown in here. So the buckling is clearly visible. Also, of course, for the slender struts, we have found the critical force by Euler, and a chart which shows the relation between the force and the horizontal displacement, which were measured using a standard displacement sensors. Of course, in order to fit that kind of module into the machine, we had to work on a loading head. This is the loading head which has a ball bearing and was equipped, the machine was equipped with it. But also because of the mechanism which I've told before, so the infinitesimal mechanism, which was shown in here, so the rotation of the upper bases, we have to enable this plate to rotate along the vertical axis, the axis of the loading. Therefore, there was a ball bearing also bind, and it was implemented into 2 cylinders, as can be seen, and therefore the finished module and the loading head is shown in this picture. A total of 12 tests were conducted, 6 tests for each type of strut, so for the stocky strut and for the slender strut, which is not shown in here. This is only a GIF, so a visible rotation. Rotation is visible by seeing that the struts are enclosing together, are getting closer together. And the measured values were the external force displacement, 3 forces in cross strings, because we had 3 force transducers, and 6 forces in base strings. Also, the rotation was measured, but I'm not showing it in here. This is the result. This is the equilibrium path, which shows the stocky strut model behavior and the slender strut model behavior. And also we can see that this is the first self-stress level, which is clearly non-self-stress, so 0. And this is the second to 6th self-stress value shown in here. We can see that pre-stressing in terms of compression is counterproductive. So in this case, it is better to not to pre-stress the model. Of course, we cannot do it because the stiffness of the model comes from the geometrical stiffness. Also, we can see that at the initial phase of the work, the both models seems to work pretty similar, but after the buckling and the initial imperfection arises, the stiffness is getting lower. Here are the results of the forces in the cross cables and base cables for the slender and stocky module. We can see here that in general, increasing the pre-stress lowers the changes of forces in the elements. That means that we can induce the pre-stress to avoid, for example, fatigue in the construction. The changes in the base cables are pretty much more visible than the changes in the cross cables. Yes. Conclusions. The presented experimental results are valuable since they are not often found in the literature, especially with force transducers on the elements. Also, for the compressive type of loading, increasing the pre-stress has a counterproductive effect on the stiffness. The higher the pre-stress, the lower the changes of all forces in elements. This may be an important fatigue factor. And there was this idea to explore the post-buckling phase in order to think of it as a emergency marker. If we design the model in a way that the buckling occurs before the rupture of the cables or the slackening of the cables. And future work, of course, is in terms of numerical validation of results. We have a model which consists of the nonlinear geometry as a whole, but I think we should approximate the struts, so the truss elements, because their behavior was nonlinear. That's all. Thank you very much.
Ladies and gents, Professor Kamiński had to leave for about 1 hour. So right now I am on duty to finish this session, but before we do that, maybe there are some questions or remarks to the authors of these presentations. Okay, so thank you very much. So right now we have a longer break, which is like 45 minutes. So longer break means longer discussions and hotter coffee. Take your time. We see you at the same place after 45 minutes. Thank you very much.